Hey guys, Eddie the Magic Monk here. I'm back with another optimization problem, and this is one step beyond what we did in the last lesson. So make sure you fully understand the first part of this tutorial before you continue with this lesson. So what is the question? The question is, find the volume of the largest right circular cone that can be inscribed in a sphere of radius r. So I have drawn the diagram for you already to show you what a right circular cone is, and basically it just means a cone with a circular base, and right just means that the tip of the cone is directly above the center of the cone. So that's what right circular cone means. And inscribed, again, similar to our last video, just means that the tip and the edges of the circle are touching the sphere. Okay, the bottom of the base of the cone is touching the edges of the sphere. Okay, so that's what the word inscribed means. Radius of the sphere is r. So that is what is making this question slightly harder than the last question. Is we're not giving a numerical value for the radius of the sphere. Okay, so usually if this question had the same difficulty as the last question, it might say of radius 5 centimeters or 6 centimeters, or give you a fixed number for radius. But it hasn't given you a fixed number, which means that we don't know what the radius of the sphere is. But what you still need to realize is that it is still a constant. Okay, it is a constant because what we're trying to change here is not the size of the sphere. It doesn't matter if the sphere is this big or if the sphere is this big. Okay, what we're trying to change here is where the cone, the length of the height of the cone inside the sphere. We're saying if we had a sphere, okay, is a cone of this high, will it have a bigger volume than a cone that is, for example, this high? Okay, which of these cones will have a bigger volume? So the radius of the sphere is not the variable here. The variable is the height of the cone. Okay, but what we do need to do is we need to relate the height of the cone to the radius of the sphere. So we need to relate these two quantities together somehow, because that is what we need to express the volume as. We need to express the volume as the radius of the sphere eventually, the maximum volume. So if you are finding this explanation a bit hard to understand, don't worry. Hopefully after you watch the rest of the video, you will have a better understanding. So let's define some variables. Okay, we have the center of the circle, and if I draw a line from the center of the circle to where the base of the cone and the sphere, the edge of the sphere is touching, we can call this the radius of the sphere. So r is the radius of sphere. Now, if I go to another center point, okay, if I go to the center of the circle on the base of the cone, right? This is the center of the base. And if I again draw a line, a straight line to the same point that the radius of the sphere is touching the edge of the cone, I'm going to call this capital R, and capital R stands for the radius of the cone, radius of base of cone. Okay, and I'm going to define a variable called h, and that is the height of the cone. So that will be this length here, that length there. The height of the cone is h. Let me just try and draw a straighter version of that. That is the height of the cone. So then what is happening is I have a little right angle triangle here. If you can see it, a little right angle triangle here. Okay, that is a right angle triangle with a right angle here. So what I can say is I can find out the relationship between the radius of the cone and the radius of the sphere using this right angle triangle. But first we need to know what this length here is. Now, because this is a sphere, the distance between the center points and the edge will be the radius. So this little distance here will just be the height. So this little distance here will just be the height of the cone minus r, which is the radius of the sphere, right? Because if you can see, this whole line is h, and this section here is r, so that means this little section here must be h minus r. So hopefully you can see that. So if I want to relate the radius of the cone with the radius of the sphere, I can now use Pythagoras theorem, which is a squared plus b squared equals c squared. So I can say h minus r squared. So h minus r here, we can say that's a squared plus b is r, and c is r squared. All right, this r value is c, the longest side of the right angle triangle. So now what we can do is we can make capital R the subject of the equation, because later on we are going to use it with the volume of a cone equation. So capital R squared is small case r squared minus h minus r squared. And I can expand that out, okay, using some simple algebraic expansion. H minus r squared is h squared minus 2hr minus r squared. Hopefully you guys remember how to expand. So then this will give me r squared minus h squared plus 2hr, plus 2hr plus r squared. This should be a plus and this should be a minus. So that is my first mistake in the video. Doing well, Eddie. So r squared minus r squared, that will cancel each other out. So then I have capital R squared is minus h squared plus 2hr. And now what I'm going to do is I'm going to write out the formula for the volume of the right circular cone. Right, if you guys remember, I have copied the notes from our last lesson. Okay, the steps for doing optimization problems. Number one, write an expression for the quantity to be optimized. In this case, it's the volume of the cone in terms of one variable. So that is the hard part. So now let's write it out. What is the expression for the volume of the cone? So volume of the cone is equal to 1 over 3 pi r squared h. Okay, 1/3 times pi times the radius of the base of the cone squared times the height of the cone. That is the volume of the cone, if you guys remember that formula. And now, if you guys can see, we have r squared in this formula. So I can substitute r squared. Okay, I can substitute this expression into where r squared is. So the answer is 1 over 3 pi times negative h squared plus 2hr times h. So now I'm going to expand all that, expand it out. So let's expand from left to right. So then it'll be 1 over 3 pi h squared negative plus 2hr over 3 pi. Okay, all of this times h. So then I have negative pi h cubed over 3 plus 2, let's just do 2 pi r h squared over 3. So we have now got an expression for the volume of the cone, and you might say, hang on, there are two variables here. There's the h, which is the height of the cone, and the r, which is the radius of the sphere. Now, if you guys remember our first discussion, the radius of the sphere, r, doesn't matter in this question. It's not about changing the radius of the sphere. The radius of the sphere is fixed. We're changing the size, we're changing the radius or the height of the cone inside the sphere. And we want to know what the maximum volume of that is. So we have actually done step one, and that was to write an expression for the quantity to be optimized in terms of one variable. So we have done that. The one variable is h, right? The radius of the sphere is a constant. So now what we're going to do is we're going to do step 2 of our optimization problem method, and that is differentiate the expression with respect to the variable. And in this case, the variable is h. So differentiating v with respect to h. So let's differentiate it. So let's use the formula for differentiating, moving the power to the front. So negative 3 over 3 pi h squared minus 1 from the power of the variable. And let's do the same thing here. So it's 4 over 3 pi rh. 3 divided by 3 is 1. So let's make that a little bit clearer. Negative pi h squared plus 4 over 3 pi rh. Okay, so now that we have differentiated it, we can go back to step 3. Find the value of x, in this case it's h, when the derivative, instead of y dash this time it's v dash, when the derivative is equal to 0. So we're trying to say when dv over dh, so when the derivative is 0, what is h? Okay, because at this point here, it's where the maximum or the minimum occurs. Okay, we're going to find out what h is, and then we're going to verify whether it's a maximum or a minimum. So 0 equals negative pi h squared plus 4 over 3 pi rh. Okay, so moving the pi h squared to the left, and then cancelling out the terms that are the same on both sides. So we got h and h. So it's h equals 4 over 3 r. And that is the relationship between the height of the cone and the radius of the sphere at the maximum or minimum volume. You can also say that r is 3h over 4. Okay, if you move the 3 to the other side and move the 4 to the other side. So now what we can do is, now that we have found the relationship between h and r at the maximum or minimum point, we want to verify if this is a maximum or a minimum. So we need to find whether it's a maximum or minimum using the second derivative test. So we now need to find d2v over dh2, or d squared v over dh squared. So that is, we need to differentiate this expression. So now I'm going to differentiate it to give me negative 2 pi h plus 4 over 3 pi r. Alright, because h is to the power of 1, so if I move the power to the front and minus 1 from the power, h disappears. So that is the second derivative of the volume with respect to the height. So let's now substitute in what r is in terms of h into the equation, so we can find out an actual value for d2v over dh squared. So d2v over dh squared would be negative 2 pi h plus 4 over 3 pi. Now the radius is, if you guys remember, the radius is 3h over 4. So let's put that in here. 3h over 4. Okay, so let's now simplify that. So it's negative 2 pi h plus 4 over 3 times pi times 3 over 4 h. So 4 over 3 and 3 over 4 will cancel each other out to 1. So it'll be negative 2 pi h plus pi h, which will be negative pi h. So that is the second derivative of the volume. Now, if you guys remember the second derivative test, and that was if the second derivative is bigger than 0, then it's a minimum. If it is smaller than 0, then it's a maximum. Okay, so because h has to be bigger than or equal to 0, right? Because, or h has to be bigger than 0, because if you guys can see in our question, there is no way that the height of the cone h can be negative. H has to be positive. So that's why, because h is bigger than 0, d2v over dh squared, the second derivative is negative pi times h, which means that it has to be smaller than 0, right? Because we have a negative number, negative 3.14, times a positive number. So negative times positive, the answer must be negative. So if the second derivative is negative, then that means that the maximum occurs at h is equal to 4 over 3 r, which is what we found earlier. Or you can say maximum occurs at r equals 3h over 4, same thing. So now what we can do is we can substitute h equals 4 over 3r back into the original equation. Okay, the original equation, which is this equation right here for the volume of the cone. We're going to substitute h back into this equation to find out the largest possible volume. So volume is equal to, should probably just copy and paste that. So let's copy this. Just paste it here. Okay, and let's substitute in h equals 4 over 3r. So v is equal to negative pi times 4 over 3r. Was that cubed over 3 plus 2 pi r bracket 4 over 3 r squared over 3. Okay, now it's getting a bit messy, but we should be able to fix that. So it's negative pi times 4 cubed over 3 cubed times r cubed over 3 plus 2 pi r times 4 squared over 3 squared r squared over 3. Okay, getting a bit tired, but it will be done. So we got negative pi times let's put all the numbers at the front, okay, because I'm getting a bit confused. So negative 4 cubed over 3 cubed pi r cubed, but we have divided by 3, so times 3 at the bottom. So really that's 3 to the power of 4 at the bottom. Okay, plus, and let's do the same thing. So I have 2 pi r, or r times r squared, that would be r cubed. And I got 4 squared at the front, so 2 times 4 squared. So it'll be 2 times 4 squared. And then over 3 squared times 3, so that would be 3 cubed. Okay, so let's try and combine that. Now, I can only combine that if the bottom are the same, so I need to multiply both the top and the bottom here by 3, so the bases are the same. So then I will have 3 to the power of 4 over here on the right as well. Okay, so this can be 3 to the power of 4, so then it'll be 3 to the power of 4, so it'll be negative 4 cubed pi r cubed plus 6 times 4 squared pi r cubed. Okay, so let's try and simplify that. So basically the bottom is going to be 3 to the power of 4, which is 81. And the top is going to be something pi r cubed, because that's the like term, so pi r cubed. It'll be negative 4 over 3 plus, sorry, negative 4 to the power of 3 plus 6 times 4 to the power of 2. Oh, this is a long tutorial. And the answer is 32. Okay, so the answer is 32 pi r cubed over 81. And that is the maximum volume of the cone with respect to the radius of the sphere. Okay, that is my final answer. Thanks for watching, guys. See you next time.